Compared to the great rivers of the world, the water of Leith here in Edinburgh is a tiny stream, but we can still see lots of evidence as to how important it's been to society over the years. The weir behind me here was built to raise the water level so that it could be used to drive water wheels that powered the industry that was formerly located in the Dean village here.
Nowadays, this particular stretch of water is an important amenity, with the pathway providing a safe route to walk or cycle to work. Engineers have had to ensure that, as development proceeds on either side, the riverbanks are protected against floods that occur with increasing frequency.
Let's look at the way the water negotiates obstacles such as the weir here. The very crest of the weir is a free overfall. There's no resistance to the flow on the downstream side. So as soon as the water has the very minimum of energy it needs to pass the weir, it plunges over in the torrent that you see behind me.
We can see this more clearly in the laboratory. Here we see water building up behind a model of a weir. The water has been coloured for visibility. As soon as it has enough energy, the water spills over the weir. The depth of water over the weir is called critical depth, and this depth is constant for a given flow rate and weir geometry. The water behind the weir is deep and slow-flowing, a form of flow known as subcritical flow. At the edge of the weir, it spills over and falls rapidly to the channel below. From the engineering point of view, what is really interesting is the shallow, fast flow on the downstream side of the weir. Here we see water with lots of kinetic energy, which could do a great deal of damage downstream if it were not handled safely. This kind of flow, the flow we get downstream of weirs and at various points in rapids in natural rivers, is called supercritical flow. This is often something that engineers need to control. If the depth and flow conditions downstream are correct, the flow can be forced to return to a slower, deeper, subcritical regime by means of a hydraulic jump. A hydraulic jump is a standing wave, typified by quite violent eddies and white water. Here we can see the supercritical flow and the hydraulic jump that forms naturally around rocks in the river. This overhead view shows the hydraulic jump running across the centre of the screen, with supercritical flow clearly visible above it. We can see the hydraulic jump again in the laboratory flume. The flow spills over the weir and becomes supercritical, but downstream the flow is restricted and a jump forms, forcing the water back to a subcritical regime. The view from the side is much more striking. The flow over the weir and the shallow, fast supercritical flow contrast with the deeper, subcritical flow downstream of the hydraulic jump. The jump itself takes the form of a jet of water close to the bed, with eddies peeling back off it to form the white water on the surface. In the field, the details are not so clear, but the basic form of the jump can still be made out. The formation and location of a hydraulic jump depend on the downstream conditions. In the laboratory, we used this adjustable sluice gate to restrict the flow out of the flume, forcing the flow to become subcritical again. We can see the hydraulic jump gradually creeping up the flume until it stabilises right against the weir. Finally, opening the sluice removes the restriction on the flow, allowing supercritical flow to continue down the flume and causing the hydraulic jump to be washed out completely.